Across the quiet plains of the solar system, long after the last of the familiar planets had cast their pale gravitational influence, something small and dim slipped across the celestial boundary. It arrived without heraldry, without cometary banners, and without the polite warning of a bright coma. It was simply there one night, an ember swept in from the dark between the stars, gliding silently into the domain of the sun. It would later be named 3I Atlas, the third known interstellar object to trespass through humanity's astronomical reach. Yet even before astronomers understood its trajectory, before they plotted its inbound arc from the immense gulf of interstellar space, some instinctive unease accompanied its presence, as though the cosmos had delivered not merely an object but a message encoded in the ice and ancient chemical breath. The mystery would not begin with its motion or its shape, but with its exhalation. For as 3I Atlas approached the warmth of the inner solar system, it did something unexpected. It awakened abruptly violently and released a burst of carbon dioxide so dense, so chemically pronounced, that its spectral signature sliced through astronomical detectors like a single discordant note in an otherwise silent symphony. It did not glow brighter in the familiar way of water ice sublimation. It did not shed dust in the gradual peeling familiar to solar system comets. Instead, its breath was dominated by CO₂, thick, heavy, and startlingly pure, an exhalation that seemed to contradict every model of how an interstellar object forged in a different stellar nursery should behave under sunlight. It was as if the object had carried within it a chamber of trapped time, a sealed vault of volatile history preserved across millions of years of stellar wandering. And when the sun touched it, that chamber ruptured. For a moment, just long enough for humanity's telescopes to glimpse the signature, the object spoke chemically, revealing something about its construction, its past, or its birthplace, yet leaving far more concealed behind its fractured, crumbling exterior. To describe the moment of its burst is to imagine a frozen traveller having drifted in cold anonymity between constellations, suddenly inhaling warmth for the first time in eons. The gases locked within its body, frozen to crystalline rigidity, in the deep interstellar void began to stir. They pushed outwards, seeping into fractures sculpted by ancient micrometeorite scars. They strained against the crust of dust and particulate grains that had gathered over unimaginable distances, and then, in a single event, brief perhaps violent, a plume of carbon dioxide erupted, a ghostly jet expanding into the surrounding vacuum. There was no atmosphere to carry the sound, but the physics of it spoke of tension, released of thermal gradients, collapsing of internal reservoirs awakening. Carbon dioxide is not unusual in comets, but its dominance is. In the solar system, CO₂ is a secondary player typically overshadowed by the sublimation of water and carbon monoxide. It is present, yes, but rarely the lead actor. For 3I Atlas, however, CO₂ was the voice, the signature, the unexpected fingerprint that declared, "I am not what you know." This solitary breath, brief as it was, kindled a strange emotional resonance. For in that plume, astronomers glimpsed not merely chemistry but lineage. They saw hints of a world long gone, a protoplanetary disk that had once circled another sun-like star, or perhaps a dim red dwarf, or perhaps something stranger still. They saw the remnants of volatile processes shaped far from the cradle that birthed Earth and Mars, and the familiar comets catalogued for centuries. They saw the possibility of cosmic diversity written not in words or symbols, but in ratios of carbon, oxygen, and ice. The event unsettled the scientific community with an almost poetic discomfort. For how could an object wandering for millions of years through harsh interstellar radiation retain such a reservoir of CO₂? How could it preserve such a composition without the protective shielding that solar system comets enjoy in their stable though frigid orbits? And what mechanism, thermal, structural, or chemical, could produce such a sudden concentrated exhalation? The scent of alien chemistry hung in the data, and yet, as with all mysteries born of distant light and fleeting encounters, the answers remained ephemeral. 3 Atlas was disintegrating, shedding mass, losing cohesion. The very act of approaching the sun seemed to unwind its structure as though the warmth was peeling back the layers of its history. Each moment revealed something new and concealed something deeper, an archaeological dig performed at astronomical distance and at the mercy of time. Still, the emotional pull of the object endured, for in every interstellar visitor lies an element of solemnity, a fragment from a place humanity will never see shaped by forces humanity will never feel arriving uninvited and departing without a trace. These objects are ambassadors from the unknown, carrying in their volatile signatures the stories of other planetary systems, stories written in chemistry rather than language. The CO₂ burst became the axis around which all inquiry would turn. It framed the mystery like a fault line running through the object's entire existence. Observatories across Earth from Hawaii to Chile tuned their instruments. Spectrographs traced the faint echo of the eruption even as the object continued its inward fall. And researchers both seasoned and young asked questions not merely of physics but of possibility. Could such a burst indicate a carbon-rich birthplace? Could it hint at processes unseen in our own solar system? Could the composition speak of a colder, dimmer star where CO₂ formed more readily, or of a disk enriched by the peculiar chemistry of early stellar evolution? The object continued its journey indifferent to human curiosity. Its motions remained governed only by gravity, its faint glow by solar irradiation. Yet its brief outgassing ripples spread across the scientific world, igniting discussions that range from astrochemistry to planetary formation to the physics of ice under cosmic conditions. In the hush of distant night skies where astronomers waited for the next spectral reading, the sense of wonder deepened. The mystery was no longer simply a question of chemistry. It had become a window, albeit narrow and fleeting, into the diversity of worlds that form beyond the sun, into the processes that sculpt frozen wanderers in alien star systems, into the ways that cosmic time preserves and reshapes matter across unimaginable distances. The CO₂-rich breath of 3i Atlas was not merely data. It was an encounter with the unfamiliar, and in that encounter, the solar system felt less like an isolated haven, and more like a single note in a vast cosmic chorus, one in which every interstellar traveller carries its own ancient melody, waiting for the warmth of a new star to coax it into song. Long before its carbon dioxide breath captivated the scientific community, 3i Atlas existed as nothing more than a subtle anomaly stitched into the nightly measurements of a sky survey. It began with a faint trace, an unassuming point of light slipping across sequential images captured by the Atlas system, the asteroid terrestrial impact last alert system perched high atop the volcanic slopes of Hawaii. Its cameras designed to safeguard Earth from hazardous objects swept the heavens, methodically cataloguing the faint motions of near-Earth asteroids. Yet on that particular night, the system identified something that did not match the quiet cadence of familiar solar system wanderers. Its movement was too swift for its distance, its arc too steep, its origin too far beyond the planetary outskirts. As astronomers reviewed the data, the object's peculiarity began to crystallize. Each new measurement refined its trajectory, and with every refinement the conclusion gained weight. The object was inbound not from the Oort cloud, nor from any reservoir of long-period comets, but from outside the sun's gravitational influence entirely. The signature of an interstellar visitor, its hyperbolic excess velocity, emerged unmistakably. It had not been born in the solar system. It had travelled through interstellar space for perhaps millions or tens of millions of years, wandering the void between stars. To understand the significance of this one must recall how rare such visitors seemed only a decade prior. Before 2017, humanity had no confirmed recordings of any interstellar object passing through the solar system. Then came Oumuamua, a strangely elongated tumbling fragment that raced past the sun with neither coma nor tail. 2 years later, Borisov, a far more comet-like visitor, followed its cyanide and carbon monoxide signatures, familiar yet still carrying the chemical accent of a foreign system. And now 3i Atlas arrived, making the once unimaginable phenomenon of interstellar trespassers feel almost routine. But this third visitor would chart its own distinct course in the story of cosmic wanderers. The early discovery photographs revealed little. 3i Atlas shone with a faint dust-muted glow typical of small icy bodies, its brightness flickering gently against the black canvas of space. Astronomers initially estimated it to be modest in size, perhaps a few hundred meters, perhaps more. Yet even these first glimpses hinted at instability. Its luminosity fluctuated more erratically than expected. At times it exhibited a faint coma, as though it were beginning to shed material earlier than its distance from the sun should justify. The detection triggered a cascade of follow-up observations. Telescopes in Chile, Spain and the Canary Islands repositioned to track the newcomer. The Minor Planet Center issued provisional designations, and researchers across the globe began cataloguing its motion. As data from different longitudes arrived, the object's hyperbolic path emerged with mathematical clarity. Its orbital eccentricity exceeded 1, the unmistakable signature of a traveller not bound to the sun. The coordinates of its arrival, its radiant point in the sky, suggested an origin somewhere near the direction of the constellation Lynx, though the precise source buried beneath millions of years of gravitational perturbations remained unknowable. But even as astronomers focused on the object's trajectory, an underlying unease threaded through the community. 3 Atlas appeared more fragile than expected, its structure perhaps compromised by internal fractures. Its brightness dipped and surged in unexpected ways, suggesting an object not stable enough to withstand significant solar heating. When compared to 2I Borisov, which displayed a surprisingly intact nucleus despite its interstellar voyage, or Oumuamua, which held its coherence despite its bizarre geometry, Thrusted Atlas seemed uniquely delicate, like a shard of cosmic frost held together by ancient cold. This fragility spurred deeper interest. If its nucleus were unstable, then any outgassing event, especially one driven by volatile ices, might reveal internal chemistry faster than with previous interstellar objects. Scientists began coordinating spectrographic campaigns to capture whatever gases emerged as the object drew nearer to the Sun. For many it represented a rare opportunity, a chance to study primordial unprocessed material, forged in a different planetary system untouched by the Sun's repeated heating cycles that shape and reshape solar system comets. The process of discovery also rekindled a fascination with the poetics of interstellar drift. For every measurement of its chemical makeup, every refined orbital parameter lay the implicit awareness that this object had crossed the dark emptiness between stars. It had survived cosmic rays that sliced through atoms one particle at a time. It had endured gravitational nudges from passing stars' molecular clouds and the unseen architecture of the Milky Way's mass distribution. It was a survivor of a planetary system's birth, a relic cast out during the tumultuous years when young planets carved paths through nascent disks. Human imagination leapt to fill the void of knowledge. Did 3I Atlas once inhabit the outer reaches of a distant solar system orbiting a young sun-like star, or was it ejected during the early instability of multiple giant planets, hurled into interstellar exile by gravitational forces too strong to resist? Or perhaps its home star was a red dwarf, a cool dim sun whose planetary system formed exotic ices, uncommon around larger stars. Each possibility painted a different origin story, each one written into the chemistry astronomers hoped to detect. As days passed, the object slowly brightened, not dramatically, but enough for larger telescopes to begin capturing clearer data. Spectroscopy teams prepared to analyze the first hints of sublimation. No one anticipated what would happen. Interstellar objects were rare, but this one behaved even more strangely than its predecessors. Its volatile emissions were not simply unfamiliar, they would soon prove to be chemically startling. But in these early moments of discovery before the CO2 burst, the focus remained logistical and observational. Each new glimpse of the object refined the mathematical arc of its path. The hyperbolic trajectory confirmed its temporary visit. It would never return. Like Borisov and Oumuamua, it had only one encounter with the Sun, and then it would vanish forever into the dark beyond Neptune's orbit. Some astronomers found in this transience a certain beauty. The object was a fleeting guest, arriving, revealing and departing in a brief cosmic heartbeat. Its presence echoed themes familiar to those who spent their nights contemplating the heavens: impermanence, distance, the fragility of celestial bodies, and the sheer improbability of tracing the journey of a rock forged around an unknown star. When 3I Atlas finally came into fuller view, showing faint signs of activity in its tenuous coma, the scientific community prepared for routine compositional analysis. After all, Borisov had shown cyanide and carbon monoxide chemistry that felt exotic, yet understandable. Oumuamua had shown almost nothing, its silence provoking more questions than answers. But 3 Atlas would offer something different, a single dramatic burst that would shatter expectations and ignite a deeper mystery. The strange flickers in brightness had foreshadowed structural instability. The predictions of imminent fragmentation gained ground, and behind the scenes researchers whispered the possibilities that this fragile shard might erupt fracture or peel away layers as it approached the Sun. The astronomers did not yet know that the first recorded hint of its deeper nature, its true strangeness would arrive not through images, but through the chemical imprint of a sudden concentrated plume. That the observation of a hyperbolic trajectory would soon give way to the astonishment of a CO₂-dominated breath. That the object, already a mystery because of its origin, would become an even greater enigma because of its composition. For now, the discovery story remained grounded in human routine, the methodical scanning of the sky, the quiet hum of servers processing nightly images, and the trained eyes of astronomers tracing the faint glow of a wanderer from the void. But the stage was set. The visitor had been found, the telescope stood ready, and the mystery of its strange breath still hidden was about to unfold. The scientific shock did not arrive quietly. It emerged abruptly like a sharp fracture in an otherwise predictable narrative, when the first high-resolution spectral data from 3i Atlas revealed a chemical profile so imbalanced, so dominated by carbon dioxide that many astronomers hesitated to believe the numbers. The spectral lines were unmistakable, narrow, resolute, brightly defined against the dim continuum of reflected sunlight. In the realm of cometary science, these signatures should have been subordinate echoes beneath the far stronger breath of water or carbon monoxide. Yet in this case, CO₂ stepped forward not merely as a detectable component, but as the lead spectral actor, its emission overpowering the contributions of other volatiles. It was a result so unusual that some teams quietly reprocessed their calibration frames, checking for contamination or instrumental artifacts. Others compared their readings with archived solar system comets, observed at similar heliocentric distances searching for precedents. They found none. In familiar comets, CO₂ is common but rarely dominant. It hides beneath the sublimation of water, which begins to flow strongly as comets warm past the frost line. Here, however, 3i Atlas released CO₂ in ratios that seemed inverted from expectation, as though the hierarchy of volatiles had been rewritten by the object's distant birthplace. This inversion was the source of the shock. In planetary science, chemical ratios are not arbitrary. They are the fingerprints of early formation environments. They encode the temperature, radiation, and dust composition of the disk from which the object emerged. To observe a CO₂-rich outgassing event of this magnitude implied that 3i Atlas had been forged in a region markedly different from the zones where cometary nuclei form within the solar system. Perhaps it condensed in a colder carbon-enriched disk. Perhaps it accumulated volatiles under pressure conditions unfamiliar to our local cosmic environment. Every possibility carried implications that stretched beyond chemistry and into the realm of exoplanetary history. The shock was amplified by the object's fragile state. Even before the CO₂ plume, researchers suspected that 3i Atlas was structurally weakened, perhaps on the verge of breaking apart. But volatile dominance in a comet's activity usually reflects its outermost ices, the ones easiest to sublimate as sunlight pours in. If CO₂ was erupting so strongly, then the outer layers must have been unusually rich in this volatile. Yet solar system comets typically bury their carbon dioxide deeper, where only gradual heating can draw it out. For 3i Atlas, the CO₂ seemed near the surface, ready to escape with minimal provocation. How could such a delicate crust survive millions of years of radiation bombardment in the void? To understand why this finding felt so disruptive, one must consider the standard expectations for interstellar objects. Exposure to cosmic rays and interstellar radiation tends to erode surface volatiles, often leaving only refractory dust or deeply buried ices intact. Over time, the uppermost layers become chemically altered, stripped of materials that sublimate easily. Borisov, for example, carried abundant CO and CN, but even these emitted in familiar ratios. Oumuamua showed no volatiles at all, suggesting its surface had long been depleted. Yet here was 3i Atlas, exhaling CO₂ as if it had scarcely been touched by its interstellar voyage. This contradiction gnawed at researchers. Was it possible that its outer layers had been shielded by a blanket of dust that only recently fractured? Could micrometeorite impacts in interstellar space have exposed fresh material mere thousands of years ago? Or did its home system contain distributions of carbon dioxide ice so unlike our own that even its superficial strata carried concentrations rarely encountered elsewhere? The burst itself, the moment of revelation, deepened the worry. It was not a gentle, steady plume like those observed in stable comets. It appeared impulsive, abrupt, as though pressure had built behind a crust, until the structural tension failed. Thermal modelling began circulating among research groups suggesting that sunlight might have penetrated a fractured region, warming trapped volatiles rapidly enough to generate internal stress. When the seal broke, CO2 surged outward, carrying dust and crystalline grains in its wake. Yet the deeper scientific shock extended beyond mechanics and chemistry. It reached into the conceptual frameworks that shaped our understanding of interstellar bodies. If 3I Atlas carried such volatile richness so near the surface, then perhaps cosmic ray erosion was not as universal or destructive as once thought. Perhaps interstellar space allowed certain types of ices to persist far longer than expected. Or perhaps most unsettling of all interstellar visitors differed from one another not merely in age or shape, but in the very principles governing their formation. This forced astronomers to grapple with a humbling realization the diversity of planetary systems might be far greater than the cautious models of a decade ago had predicted. Beyond the gravitational reach of our Sun lay worlds where chemical processes favoured unusual volatiles, where pressure and temperature sculpted icy bodies into forms unfamiliar in the solar system, and where cometary nuclei developed layered structures that resisted the degradations of interstellar travel. Such implications touched the core of astrochemistry. If 3I Atlas formed in a carbon-enriched disk, what did that mean for planet formation in its home system? Did rocky planets form with thicker CO2 atmospheres? Did its worlds contain exotic ices beneath their surfaces? And what of habitability did such distributions favour or hinder the development of life? These questions remained speculative, but the shock remained grounded in data. The spectral lines were real, the ratios were real, the object's instability was real, and the explanations, though varied, all pointed toward the same unsettling conclusion. 3I Atlas was built from materials and processes unlike anything routinely encountered in the solar system. Astronomers found themselves facing a new category of cosmic visitor, not merely interstellar, but chemically alien. The burst framed the object not as a simple wanderer, but as a messenger bearing an unfamiliar chemical dialect. Its CO2 breath did not just challenge prior expectations, it undermined the assumption that interstellar objects would fall within familiar boundaries. It suggested that some could carry the signatures of extreme environments, cold pressures, carbon-rich chemistry, or deeply stratified ice layers that defy solar system parallels. The shock spread quickly through conferences and astronomical forums. Some researchers found themselves revisiting archival data from Borisov, wondering if subtler hints of unusual volatiles had been overlooked. Others drew comparisons to primordial solar system models, attempting to imagine how different the chemistry might appear if our own star had formed in a carbon-enhanced molecular cloud. But no theoretical reconstruction provided a simple answer. The peculiarity of 3I Atlas remained, an object fractured by sunlight exhaling carbon dioxide with unexpected dominance and slowly disintegrating as it descended toward the sun. The scientific shock lingered not because the data contradicted existing models, but because it suggested those models were far too narrow. The cosmos was telling a larger story, a story in which interstellar wanderers carry chemical memories of worlds humanity may never witness. And 3I Atlas, with its startling CO2 plume, had just spoken one of those ancient alien memories aloud. In the days that followed the initial spectral shock, the deeper investigation into 3I Atlas began in earnest. What had first appeared as a fleeting anomalous signature now demanded a systematic excavation of the object's chemical identity. The comet, if one could even call it a comet in the familiar solar system sense, was disintegrating. Each passing hour under solar heating stripped more material from its surface, peeling away layers that had remained untouched for millions of years. Yet this fragility was paradoxically a gift. With every fragment lost, 3I Atlas revealed more of its story, scattering its secrets into the light of telescopes across Earth. The first priority was to confirm the CO2 measurements. Multiple observatories repeated their observations at different wavelengths, cross-checking one another with the precision of forensic investigators. The results converged with striking consistency. Carbon dioxide emissions dominated the volatile output, overshadowing signals from water carbon monoxide and other expected species. In typical comets, as solar radiation heats, the nucleus water vapor is usually the main driver of activity, boiling off lifting dust and forming the coma. Carbon monoxide often appears at greater distances from the sun due to its lower sublimation temperature. Carbon dioxide, meanwhile, tends to rise in prominence only near intermediate distances, forming part of a blended chorus rather than a solitary voice. But 3i Atlas displayed none of this balance. Instead, the CO2 signal arrived like a floodlight illuminating the faint trail of the inbound traveller. It overpowered the weaker whispers of water and carbon monoxide, revealing a nucleus built on volatile priorities alien to those known within the solar system. The anomaly forced scientists to re-examine their assumptions and consider models of ice formation in environments far colder or perhaps chemically distinct from those known around the Sun. Comparisons to Oumuamua and Borisov became inevitable. Oumuamua, the first interstellar object, had offered almost no volatile emissions at all. It behaved more like a desiccated shard stripped of its outer layers, its surface altered by radiation during eons of interstellar wandering. Borisov, on the other hand, had acted almost too familiar. Its chemistry resembled that of a dynamically new solar system comet, with cyanide and carbon monoxide emissions aligning closely with known patterns. 3i Atlas fell somewhere in between, yet also far outside this emerging spectrum. It was active like Borisov, but its activity was dominated by a volatile signature, unfamiliar even among the more exotic solar system models. Detailed spectrographs began revealing additional subtleties. The ratios of CO2 to water, normally a key diagnostic of cometary composition, hovered at levels so extreme that some teams questioned whether 3i Atlas possessed a water-rich surface layer at all. The spectral lines for H2O were faint, nearly drowned beneath the bold CO2 signature. Meanwhile, the expected presence of OH, an indirect tracer of water sublimation, contributed only modestly to the overall spectrum. It was as if the object's outermost layers had been sculpted from a fundamentally different blueprint. This disparity prompted deeper investigation into the physical mechanisms at play. Thermal models suggested that for carbon dioxide to dominate so strongly, the upper strata of the nucleus must contain unusually high concentrations of CO2 ice. In the solar system, such ices often exist deeper within the nucleus, accessible only once the outer dusty shell has been eroded by repeated perihelion passes. Yet an interstellar object travelling through the cold vacuum between stars for millions of years should have lost its most volatile materials early in its journey. Cosmic rays and interstellar ultraviolet light, unshielded by any atmosphere or magnetic field, tend to disassociate molecules and erode icy surfaces. Many had assumed that interstellar objects reaching the solar system would be desiccated remnants, quiet stones, carrying only the memory of their original chemistry. But 3i Atlas defied this expectation. The CO2 clearly survived. And not only survived, it appeared abundant, accessible, and energetically poised for release. When the sun's heat finally reached the object, its internal reservoirs did not respond gradually, they ruptured. This rupture marked an inflection point in the investigation. For if CO2 existed so near the surface, one needed to consider how deeply the volatile layers extended. Could the burst have been the result of a pocket of gas sealed beneath a thin crust? Did 3i Atlas contain stratified layers formed during its original accretion phase, now exposed by interstellar erosion, or had cosmic rays ironically preserved CO2 by chemically altering surrounding materials into forms that acted as a protective matrix? In the wake of the burst, telescopes turned their attention to the dust released alongside the gas. Dust grains carry mineralogical fingerprints of their parent body's interior. Polarimetric analysis revealed that the grains were unusually fine, suggesting a fragile matrix that crumbled easily under thermal stress. Some grains possessed high carbon content, hinting at organic rich chemistry, less common in many solar system comets, but plausible in carbon-enhanced disks around other types of stars. Infrared observations suggested the presence of amorphous silicates, mixed with volatile rich ice particles materials that had not been annealed or processed significantly since their formation. The investigation deepened further when rotation models revealed irregular tumbling motions. Such chaotic rotation often reflects internal mass loss, or structural asymmetry signs that the nucleus was fragmenting beneath the stress of solar heating. The CO2 burst likely accelerated this instability, pushing the object into a more chaotic spin and hastening its disintegration. This slow unraveling provided additional clues as different layers of the nucleus became exposed over time, offering further glimpses into its internal chemistry. Some researchers modelled how the CO2 burst might have affected the object's trajectory. Non-gravitational accelerations, minute but measurable, shifted the object's path subtly, making precise orbital predictions more difficult. These changes added another puzzle. The outgassing force required to produce the observed accelerations seemed disproportionate to the measured dust output. This discrepancy suggested that the CO2 jet had been even more powerful than initial models assumed, or that additional less detectable volatiles were involved in the event. The deeper investigation also compelled astronomers to examine the object's thermal inertia, its ability to conduct heat through its structure. Some models suggested that 3I Atlas had extremely low thermal conductivity, meaning sunlight heated only its outermost layers while leaving the interior extremely cold. This could create localized stress points where pockets of CO2 warmed just enough to expand remain trapped beneath frigid insulating layers. Over time, such pressure could build into a sudden eruption like steam trapped beneath a frozen lake, finally breaking through the ice. Still, none of these models fully resolve the core question why so much CO2 and why so readily accessible. The deeper scientists looked, the more the puzzle seemed to expand. Every data point brought clarity to the singular event, yet also widened the conceptual distance between 3I Atlas and known cometary analogues. The object was teaching astronomers something fundamental about the chemistry and physical evolution of worlds beyond the Sun, something they could not yet articulate but sensed in the strange interplay of its volatile breath and crumbling structure. The investigation was far from over. The CO2 burst had not solved the mystery, it had merely excavated the first layer. Beneath it lay deeper questions waiting to be unearthed. As 3I Atlas drifted deeper into the realm of the Sun, its behaviour grew increasingly erratic. What had begun as a spectral anomaly now revealed itself as a dynamic puzzle, a cascade of physical deviations hinting that the strange CO2-rich burst was not an isolated event, but part of a larger instability unfolding within the object's fractured core. Astronomers watched its trajectory, closely tracing the faint curvature carved by gravity sunlight and the subtle, uneven push of its own escaping volatiles. Yet with each new set of measurements, the motion of the interstellar wanderer seemed to slip further from predictability, as if the object itself were resisting the ordered paths expected of celestial bodies. Its orbit was hyperbolic, unmistakably the arc of a visitor passing through the solar system only once. Yet the fine details, those small departures from a purely gravitational path, began to attract attention. Non-gravitational accelerations, tiny deviations caused by asymmetric outgassing, were common enough in comets, but the pattern for 3I Atlas did not align with the traditional profiles. Water-driven jets typically dominate such behaviour. They follow predictable thermal gradients strongest on the sunlit face of the nucleus. But the CO2 burst had altered those expectations. The object's acceleration did not match models driven by water sublimation. Instead, it suggested thrust from a source that was deeper, more abrupt, and possibly directional in a way the Sun alone could not easily explain. The rotation of 3I Atlas provided further clues and further confusion. By analysing its light curve, astronomers attempted to decode how the object was spinning, expecting to uncover a coherent rotation period. Instead, they found irregular, uneven fluctuations in brightness, as though the nucleus were tumbling chaotically, shifting its orientation unpredictably. Such tumbling suggested a recent disturbance. A sudden burst of CO2 erupting through a weakened crust could have imparted torque, destabilizing the object's spin. But the degree of chaos hinted at deeper structural fractures, perhaps running through the nucleus like fault lines. Each shift in brightness hinted at surfaces turning unpredictably toward the Sun, exposing new layers of volatile ices and triggering further bursts too faint to detect individually, but strong enough to push the object off course. The motion became a dance of fragile equilibrium gravity pulling it inward, sunlight heating its fractured surfaces, and the object responding with small exhalations of gas that nudged it sideways, altering its path like a feather caught in a windless drifting world. The disintegration of solar system comets had offered an analogue, though only imperfectly. Comet Ison, for example, had brightened and fractured catastrophically as it neared the Sun, its nucleus unable to withstand the heating. Yet 3I Atlas was doing something different. Its fragmentation did not appear to be driven solely by thermal decay. It seemed to be accelerated by the strange volatile-rich layers hidden within its structure. The CO2 dominance reshaped the sequence of its decay, pushing its behaviour outside the familiar bounds of cometary physics. Dust expelled from its surface, normally a reliable indicator of cometary activity, behaved unusually. Observations showed that the dust coma was far less dense than would be expected from such a strong gas burst. Typically, dust follows gas as volatiles sublimate. They carry particulate grains into space, forming a diffuse tail. but 3i Atlas released comparatively little dust relative to its CO2 output, suggesting either that the burst originated from a pocket lacking solid grains, or that the dust was confined to extremely fine particles too small to scatter significant light. The object's faint tail reflected this imbalance. Rather than a sweeping arc of dust shaped by the solar wind, its tail appeared thin, almost ghostly, as if the sun's warmth could coax gas from its interior, but could not lift substantial particulate matter with it. This delicate morphology hinted at structural weakness, a nucleus whose cohesive forces had long since faded during its interstellar journey. Dust grains may have been too loosely bound to survive intact fracturing into microscopic fragments before they had time to escape into space. The fine-grained dust clouded the area around the object, scattering light in subtle patterns that suggested ongoing erosion even in the absence of strong outgassing. As these anomalies accumulated, a deeper unease settled among the researchers following the object. Every new data point seemed to widen the conceptual distance between 3i Atlas and the familiar behaviours of solar system comets. The burst, the rotation, the dust patterns, they all pointed to an object that was not merely unusual, but fundamentally different in its internal architecture. Some models began to propose that the nucleus might consist of loosely aggregated clumps, held together more by cold adhesion than by dense structural bonding. A nucleus composed of such fragile conglomerates could fracture easily, leaving cavities where CO2 might accumulate and erupt. The question of the object's density became a topic of intense study. Light curve modelling suggested a density far lower than that of typical cometary nuclei, perhaps even lower than some of the most fragile sun-formed bodies. Such low density implied a highly porous structure, an icy matrix riddled with voids formed during its accretion period, perhaps shaped by the slow, gentle collisions characteristic of early protoplanetary disks. This porosity could explain the uneven outgassing sunlight might penetrate the upper layers more deeply than expected, heating pockets of trapped CO2 unevenly causing sudden ruptures that realigned not just the object's rotation, but its broader trajectory. Even more intriguing was the possibility that the strange CO2-rich burst represented only one instance in a series of pressure-driven events occurring across the nucleus. The brightness fluctuation suggested multiple jets activating intermittently, each responding to unpredictable exposures of new volatile-rich surfaces. Yet none of these subsequent jets matched the magnitude of the initial burst, leaving astronomers to wonder whether the first eruption had vented the majority of the accessible CO2 or whether deeper reservoirs waited behind thicker insulating layers. The irregularities extended beyond chemistry and motion. Observations in the infrared spectrum hinted at an unusual thermal profile. Parts of the object warmed more rapidly than expected, while others remained cold even under direct solar illumination. This thermal asymmetry could reflect compositional heterogeneity, with different regions containing different volatiles' grains and densities. Or it could reflect a surface layered unevenly through interstellar erosion, where micrometeorite impacts and radiation had sculpted a patchwork of materials with varying thermal conductivity. Such complexity transformed the investigation into an astronomical autopsy performed in real time. Researchers were forced to read the object's behaviour like forensic clues, the faint acceleration of its path, the low-density dust drifting from its surface, the thermal flickers across its rotating form. Each piece suggested that the CO2 burst was not merely a chemical oddity, but a structural indicator, a sign that the interior of 3i Atlas had evolved in an environment unlike those that shaped solar system bodies. The broader implications of these anomalies reached beyond the object itself. If interstellar visitors could vary this dramatically in their internal chemistry and structure, then the diversity of exoplanetary systems must be equally vast. 3i Atlas might represent a frozen fragment of a carbon-enriched protoplanetary disk, or the residue of a world shaped under a dimmer star where CO2 condensed more readily. Or it might be a survivor from the volatile-rich outer zones of a system whose early development bore little resemblance to that of the Sun. But as the mystery deepened, a darker possibility emerged that 3i Atlas was not simply different, it was decaying rapidly. The chaotic tumbling, the faint dust, the erratic outgassing, all implied that the object might not survive its passage near the Sun. Some models predicted that it would break into smaller fragments before reaching perihelion. Others suggested it might disintegrate entirely, leaving only a faint stream of dust and gas to mark its once coherent form. If that happened, the interstellar visitor's secrets would scatter irretrievably into space. The growing instability visible in every observational dataset underscored the urgency of the investigation. Researchers knew the window to study 3I Atlas was narrowing. Soon its motion, its structure, and its chemical breath would slip beyond reach. Yet in its instability and the unpredictable way it responded to the Sun, 3I Atlas revealed its identity more clearly than any stable comet could. Its anomalous motion shaped by the strange CO₂-rich burst, and the fragile architecture beneath its surface exposed the deeper riddle that the object was composed of materials from a place fundamentally unlike the solar system, shaped by forces and conditions no terrestrial scientist had yet experienced. The mystery did not simply deepen, it expanded, pushing the boundaries of cometary science toward new uncharted territory. Beneath the fractured surface of 3I Atlas, beneath the dust that scattered weakly into space, and the erratic jets that twisted its path, astronomers sensed the presence of layers long hidden from the light of any star. The strange CO₂ eruption was not merely a chemical surprise, it was a revelation of interior architecture. Whatever lay within the nucleus could no longer be dismissed as ordinary cometary ice. It forced investigators to consider what structures might form in the cold womb of a distant protoplanetary disk, and how those structures might survive an unthinkably long exile in interstellar darkness. To pass those layers, researchers turned first to the physics of volatile entrapment. In the solar system, comets contain a mixture of crystalline and amorphous ices, water carbon monoxide, carbon dioxide, methanol, and traces of complex organics held together in a fragile matrix. But the proportions and physical states of those ices depend heavily on the temperature of their birth. At around 30-50 Kelvin, water remains amorphous, locking other molecules into its structure like insects caught in sap. As temperatures rise above 130-150 Kelvin, that amorphous ice transitions into a crystalline lattice, releasing trapped gases in sudden pulses. If 3I Atlas formed in an extremely cold region of its home system, vast quantities of CO₂ could have been imprisoned in amorphous water ice, held inert for millions of years, until the sun's warmth reached it. The violent burst might then have been a crystallization event, a sudden restructuring of its internal ice that expelled trapped volatiles with explosive force. This model carried explanatory weight, particularly given the abruptness of the emission and the object's apparent structural fragility. But it raised a question of its own. Why did the emission appear overwhelmingly dominated by CO₂, when trapped gases typically emerge as mixtures? To address this, researchers proposed a more complex internal layering. Perhaps 3I Atlas once orbited a star with unusual chemistry, a star whose protoplanetary disk contained higher concentrations of carbon-rich dust, or CO₂-heavy ices. In such an environment, the layers formed during accretion might separate volatiles into distinct strata. One layer could be rich in CO₂, another in CO, and deeper layers in water ice. If the crust above a CO₂-dominated layer fractured first, then that layer alone might erupt, producing the singular burst observed. This possibility gained traction as infrared and ultraviolet observations revealed uneven temperature distributions across the object's surface regions, warming at different rates as though different materials sat beneath different patches of crust. Some models attempted to map these patches into a mosaic of volatile reservoirs, each waiting to activate as sunlight penetrated deeper. The deeper the investigators looked, the more they saw hints of heterogeneity. A slowly disintegrating nucleus is a kind of natural excavation, each lost fragment peeling away layers that had been shielded from starlight since the object's formation. When 3I Atlas shed dust into space, the particle sizes revealed information about the bonds holding its structure together. The grains were extremely fine, far finer than typical dust from solar system comets, suggesting a nucleus that had never undergone the thermal cycles necessary to sinter its materials into stronger structures. This fragility pointed to a life spent entirely in deep cold, its layers undisturbed since their original assembly. Grain composition added another clue. Spectroscopy of the dust cloud revealed a higher than expected presence of carbon-bearing compounds, including complex organics. These materials often accumulate in regions with rich carbon chemistry, such as the outer zones of protoplanetary disks around carbon-enhanced stars. If 3I Atlas had accreted in such a disk, the layers beneath its surface might reflect a chemical environment fundamentally different from the Sun's. Such a birthplace would help explain the CO₂ abundance in disks where carbon is plentiful relative to oxygen, carbon dioxide could form more readily settling into icy layers early in the accretion process. If the object's building blocks contained CO2 as a major component rather than a trace, the resulting nucleus would naturally hold CO₂-rich bands mixed unevenly with other volatiles. But the structure of 3I Atlas likely involved more than mere chemical ratios. Over millions of years drifting through interstellar space, cosmic rays would have penetrated its outer layers, chemically altering them, and perhaps compressing certain volatiles into denser pockets trapped beneath irradiated crust. Cosmic ray processing tends to erode surfaces, but can also create hardened layers of organic-rich material. These layers may act as barriers sealing in volatile deposits beneath them. If such a barrier formed over a CO₂-enriched region, pressure could build as the object warmed until a fracture allowed the gas to escape violently. To test this possibility, thermal inertia models were developed simulating how heat would travel through a porous icy body. Many models converged on the same conclusion. The outer crust of 3I Atlas likely acted as an insulator of remarkable effectiveness, preventing deep heating even as the surface warmed rapidly. The sun's energy might create a thin layer of warm material atop a sub-zero interior, encouraging volatile pockets nearer to the surface to activate first. If those pockets were disproportionately rich in CO2, then the eruption would indeed be dominated by that gas. Another layer-based hypothesis explored the dynamics of phase transitions. At extremely low temperatures, CO2 can exist not as crystalline ice, but as Clathraett's molecular cages in which gas molecules are trapped within a lattice of water ice. These structures release their gases abruptly when destabilized, producing surges of volatiles, capable of reshaping a comet's rotational trajectory. If 3I Atlas contained CO2 clathrates near its surface, their destabilization could explain the sudden directional jet observed. Yet each hypothesis, amorphous ice transitions, clathrates, cosmic ray crusts, carbon-rich birth environments solved only part of the puzzle. None explained the full intensity of the CO2 dominance, nor the extreme fragility of the nucleus, nor the faintness of its accompanying dust cloud. The pieces fit together loosely like fragments of a puzzle missing its central image. This uncertainty drove investigators deeper into speculation, guided not by guesswork, but by increasingly sophisticated models of planetary formation in unfamiliar environments. Could 3I Atlas have formed in the outer disk of a low metallicity star where water ice was scarce? Could it have originated in a binary star system, where gravitational instabilities concentrated CO2 into localized reservoirs, or might it have formed closer to its star, then been ejected before repeated heating cycles could remove its volatile layers? Each model reshaped the layers imagined beneath the surface. In some versions, CO2 dominated because the object formed in a disk, with unusually low water vapor content. In others, turbulent mixing segregated volatiles during accretion trapping CO2 beneath porous dust layers. In still others, shocks within the disk created pockets of enhanced CO2 that froze quickly into solid layers. As the models proliferated, each pointing to different interior structures, one theme resurfaced repeatedly. 3I Atlas was likely the product of a chemical environment distinctly unlike that of the solar system. Its layers, rich in CO2, fragile in structure, irregular in temperature response, seemed to carry the imprint of a world humanity would never see. Perhaps the most evocative image emerged from the idea of stratified volatile bands, a nucleus built like a frozen palimpsest. Each layer formed during a different epoch of its star's early life, each layer holding different ices, dust grains and trapped gases. Over millions of years drifting through the void, cosmic rays etched away its outermost lines, but deeper inscriptions remained intact. And when the sun's warmth touched those buried stories, one of them written in carbon dioxide burst free, revealing a fragment of the object's ancient origin. The investigation into these layers became a meditation on distance and time. For beneath its fragile crust, 3I Atlas carried echoes of a world lost to the cosmos' volatile signatures that no telescope could fully interpret, but which pointed toward a diversity of planetary architectures far beyond the solar system's familiar blueprint. And as researchers probed deeper into these hidden structures, they realized the mystery was not simply scientific, it was archaeological. 3I Atlas was not just a visitor, it was a fossil, a layered chronicle of a star system long vanished from its site. As 3I Atlas drifted closer to the sun, its fragile nucleus entered a region of illumination it had never known. For millions of years it had wandered through darkness so complete that only the faint glow of distant starlight brushed its surface. Now, sunlight, intense, radiant, and unfiltered, poured across the object's fractured form. This thermal awakening did more than illuminate the surface. It reshaped it. Heat seeped into cracks carved by cosmic rays, pressed into cavities formed during accretion, and triggered dormant mechanical stresses that transformed the interstellar visitor from a silent wanderer into a volatile, unstable body. It was in this delicate threshold between cold endurance and sudden collapse that astronomers began to suspect the role of exotic ice's substances that behave unpredictably under rapid warming after eons of cryogenic stillness. No solar system comet had ever offered a direct analogue. In familiar comets, solar heating follows predictable behaviour. Water sublimates. As the temperature rises, carbon monoxide emerges in more distant regions, and dust lifts into the coma with structural consistency. But 3I Atlas appeared to have been sculpted from a mixture of volatiles unfamiliar in such accessible abundance. The dominance of CO₂ had already signalled a chemistry far from ordinary. Now, its physical responses suggested that the nucleus housed ices that behaved differently from those typically observed around the Sun, ices that had been preserved at temperatures so low they rarely persist near star-forming regions. The concept of exotic cryogenic behaviour was not speculation born from imagination, it was grounded in physics. At temperatures below 30 Kelvin common in the outer disks of cold, dim stars, or the shadowed outskirts of protoplanetary systems CO₂, Cu, and other gases can freeze into amorphous matrices or clathrate structures far more delicate than crystalline water ice. These ices remain locked in rigid stillness until a sudden influx of heat destabilizes them. When destabilization occurs, the response is not gradual sublimation but sudden transformation. Gases are expelled rapidly as the structure collapses, sometimes violently. This mechanism fit the abrupt CO₂ burst witnessed from 3I Atlas with uncanny precision. If the Sun's warmth had penetrated just far enough to trigger a phase change in near-surface CO₂-rich regions, the result would be exactly what astronomers observed: a sudden release, an eruptive plume, a rearrangement of the object's rotation. But the behaviour did not end there. Instead, the comet began to fracture further, hinting that the burst had initiated a chain of internal collapses. Thermal stress emerged as a central culprit. As sunlight warmed one hemisphere, while the other remained frigid temperature gradients spread across the nucleus. In any icy body, these gradients generate internal tensions. But in a body composed of volatile, rich, amorphous ice, porous dust aggregates, and delicate molecular cages, these tensions grow unpredictable. Cracks propagate unevenly, pockets of trapped gases expand, and fractures open pathways between layers previously sealed from the surface. In the context of 3I Atlas, these pathways could have connected deeper volatile reservoirs with the surface, exposing CO₂ that had remained insulated for geological time. The slow propagation of these cracks combined with the chaotic tumbling observed suggested that as the object rotated, different fractured regions were exposed intermittently to sunlight. Each exposure introduced new opportunities for sudden sublimation, venting, or surface collapse. The fragility of the nucleus supported this interpretation. Dust expelled from the object consisted mostly of ultrafine grains, potentially a sign of cryogenic fracturing rather than thermal erosion. In near absolute zero environments, ices and dust grains fuse weakly, forming tenuous lattices that crumble easily when warmed. Such fragile structures are rarely preserved in solar system comets, which endure cyclic heating and cooling. But an interstellar object drifting through deep cold could maintain these exotic bonds indefinitely, until the heat of a star abruptly awakened them. Astronomers also considered the role of internal pressure. If the CO₂ burst originated from a cavity sealed beneath more rigid crustal layers, perhaps layers hardened by cosmic ray processing, then warming could have caused a buildup of vapor pressure beneath the crust. Once this pressure exceeded the tensile strength of the overlying material, the crust would rupture, sending gas streaming violently into space. In such a scenario, the structural integrity of the nucleus would degrade rapidly, leaving it vulnerable to tidal stresses and continued thermal fracturing. The chaotic rotation of 3I Atlas offered supporting evidence. The torque imparted by the CO₂ eruption appeared sufficient to disrupt any stable rotation the nucleus once possessed. Subsequent thermal fluctuations would only exacerbate this spin-state instability, forcing the object into an uneven tumbling motion. With each chaotic turn, poorly supported regions of the nucleus might shear away, revealing new cryogenic layers that would react unpredictably to exposure. Another consideration lay in the nature of CO2 itself. When trapped in interstellar ices, CO2 molecules can form unusual crystalline or amorphous arrangements, influenced by the presence of impurities like methane N2 or CO. Upon heating, these composite ices undergo complex transitions, releasing their constituent molecules in different sequences depending on local temperatures and pressures. A CO2-dominated layer enriched with such impurities could erupt with disproportionate force compared to its mass, providing an explanation for the burst's intensity, despite the object's relatively low dust output. Even the tail's faintness contributed to the developing picture. A burst driven primarily by gas rather than dust would produce minimal particulate release, matching exactly what telescopes observed. The gas would flash outward in a directional plume, while the dust, if weakened by thermal shock, might fragment into grains too fine to reflect significant light, contributing little to the visible tail. As thermal models refined the scenario, investigators began constructing an image of an object undergoing catastrophic internal reorganization. The CO2-rich burst was not a single aberration, but the first domino in a chain of structural unravelings. The sun's heat, indifferent and steady, penetrated deeper with each passing day. Cracks expanded, temperature gradients intensified, layers of volatile and exotic ices shifted under the stress, preparing for additional releases, and underlying it all was the haunting conclusion that these exotic behaviours were not merely quirks, but signatures of an environment far colder, chemically different and structurally alien compared to the solar system's birthplace. Thrice Atlas had been shaped in a cradle where CO2 froze in quantities rarely observed here, where dust grains accreted under temperatures colder than any region near the sun, and where its layered structure evolved under conditions absent from human experience. What astronomers witnessed was a form of cryovolcanic awakening, but one from a body that had never belonged to the sun. The strange CO2-rich burst was simply the first revelation of these alien ices. As the nucleus continued to unravel, it offered one more profound reminder: the materials that form worlds around other stars may behave in ways entirely beyond solar system intuition. And only when such material is exposed to the unfamiliar warmth of our sun do those behaviours reveal themselves, erupting into view like the breath of a world long lost. The deeper astronomers probed into the unfolding behaviour of Three-Eye Atlas, the more the data resisted the comfort of familiar patterns. Instead of converging toward a coherent model, each new observation pushed the puzzle into more disquieting terrain. The original CO2-rich burst had been startling enough, but the weeks that followed revealed something even more unsettling: the ratios of volatiles, CO2, CO, H2O, and their photodissociation products refused to align with any known evolutionary path for cometary bodies. What should have followed the eruption, according to solar system analogues, simply did not. The object seemed intent on contradicting expectations at every turn. In the wake of the initial plume, astronomers anticipated a steady increase in water vapour as the nucleus warmed. Yet water remained faint, almost hesitant, as though it existed only in thin, depleted layers. The expected rise in OH emission, a secondary tracer for sublimating water, barely registered. Carbon monoxide, which often accompanies CO2 activity in distant comets, was present but unexpectedly weak. The imbalance deepened with each spectral sweep. Instead of stabilizing around a predictable composition, the object's chemical output fluctuated erratically, as though different layers were being exposed piecemeal by ongoing fractures. It was the persistence of CO2 dominance that confounded researchers. After such a powerful initial burst, the standard expectation was that deeper, more mixed volatiles would take over the activity. But Three-Eye Atlas continued to exhale CO2 with disproportionate strength, as if the nucleus contained multiple strata, each one heavily enriched in the same gas. In solar system comets, CO2 rarely occupies such a large fraction of the near-surface inventory, and when it emerges, it does so alongside water and CO in broadly varying proportions. The consistency of the anomaly suggested not a single pocket but a recurring geological feature. To some researchers, this was the most troubling sign. The persistent repeating pattern pointed to an object formed in a disk where CO2 was not merely present, but abundant and crucially preserved through processes that should have erased such features during its interstellar exile. The notion that the object's volatile structure had remained so intact, even after being exposed to cosmic rays for millions of years, forced a reconsideration of long-held assumptions about how interstellar space alters small bodies. Every model attempting to simulate cosmic ray processing predicted the opposite outcome. CO₂-rich outer layers should degrade over time, converting into carbon monoxide or more complex carbon chains. Volatile reservoirs near the surface should empty slowly, leaving only refractory materials. Yet here was an object whose surface layers, if its emissions were to be believed, retained their volatile richness, like a time capsule shielded against the galaxy's radiation. This contradiction struck at the foundations of cometary science. Either 3i Atlas had spent most of its life shielded by an unusually thick protective crust, or it had undergone some bizarre evolutionary path unlike anything seen in the solar system. Neither explanation rested comfortably within existing models. Even more striking were the thermal lag patterns emerging from the light curve analysis. As the nucleus rotated, certain regions brightened with a rhythm that did not correspond solely to solar illumination. Instead, the fluctuations hinted at delayed heating subsurface layers, warming long after expected, rupturing at unpredictable intervals and releasing volatiles inconsistent with the immediate temperature profile. This thermal lag pointed to deep cryogenic insulation, perhaps from ultraporous layers, or trapped volatiles embedded in matrices unlike those known from solar system ices. Meanwhile, the object's fragmentation accelerated. At first, small pieces of the nucleus appeared to drift away, faint glimmers of reflected sunlight marking their slow departure. But soon the disintegration became less subtle. Entire chunks seemed to shear off, drifting as discrete bodies. This degree of instability was unusual but not unprecedented. Comet Ison had behaved similarly before its death near the Sun. Yet the chemistry did not match Ison's water-driven disintegration. Instead, 3i Atlas seemed to break apart preferentially along regions tied to CO₂ sublimation and thermal fracturing. The visible structural decay aligned not with ordinary heating patterns, but with the peculiar chemistry driving the object's activity. This raised the unnerving possibility that 3i Atlas had internal fractures aligned along chemical boundaries, bands of materials so distinct that they formed geological fault lines weakened by differential thermal expansion. Each shift in rotation exposed a different chemical stratum to sunlight, generating a staggered sequence of eruptions and structural failures. One hypothesis attempted to unify the data. Perhaps 3i Atlas formed in a region of a protoplanetary disk that experienced periodic cold shock events. In such environments, rapid temperature drops could freeze CO₂ into distinct pure layers, trapping them beneath dust and other volatiles. Subsequent slow accretion might bury these layers unevenly within the nucleus. If true, the object could contain multiple CO₂-rich strata, each waiting to be exposed by the progressive unraveling of the nucleus. But here too, the hypothesis faltered. Solar system formation models contained no known analogue for such repeated cold shock events, occurring at scales that would build layered CO₂ strata. It required physical conditions far more extreme, perhaps, near the outer edge of a disk around a variable star or within a region influenced by turbulent gas flows. The speculation drifted toward exotic astrophysical environments seldom explored in cometary contexts. Other researchers proposed a more radical idea that 3i Atlas might have originated not in the outer disk of a star but in the remnant outskirts of a system undergoing late-stage dynamical instability. If the object had once been part of a larger body, perhaps even a dwarf planet-sized world, then its internal structure might carry relic stratification from geological or cryovolcanic processes. Layers of CO₂ ice could have formed in subsurface reservoirs later shattered and dispersed into space by a catastrophic collision or gravitational ejection event. Under such a scenario, 3i Atlas would be a fragment, a shard from a much larger parent world. The chemical inconsistencies supported such an origin. The faint presence of CO and the suppressed water signature aligned with scenarios in which water ice sublimated away long before ejection, while deeper CO₂ pockets remained shielded. Yet if this were the case, then the object's survival through interstellar space preserving such delicate chemistry became even more unlikely. How could a fragment of a shattered world survive intact for millions of years, its volatile reservoirs unspoiled? This question hung over every new observation, deepening the mystery. Meanwhile, models trying to estimate the object's original mass and cohesion produced contradictory outcomes. Some suggested that 3I Atlas had once been much larger, shedding material slowly over its interstellar journey. Others indicated that its current fragile state was primordial, that it had always been a loose agglomeration of ices unable to endure even modest thermal stress. Each scenario carried different implications for its birthplace and chemical evolution. All the while, the mismatched ratios persisted. The more astronomers measured, the more the chemical profile defied categorization. Even the dust-to-gas ratios, normally stable indicators of cometary behavior, fluctuated wildly, showing periods where dust emission nearly ceased while CO2 surged dramatically. The dust that did appear grew increasingly fine, hinting at deeper layers composed of even more fragile materials. Thermal models strained to explain the minimal dust lift despite the volatile richness. Mechanical models struggled to reconcile the object's rapid fragmentation with the irregular but powerful gas outbursts. As this contradictory data accumulated, one conclusion grew increasingly unavoidable. Whatever 3I Atlas was, it was not simply a comet by solar system standards. It belonged to an entirely different category, an object shaped by conditions no human instrument had previously sampled, forged in environments whose chemical rhythms diverged sharply from the familiar choreography of water-driven sublimation. The escalating contradiction between data and expectation carried a quiet, sobering message. The diversity of small bodies in the galaxy was far greater than assumed. Interstellar objects were not merely foreign, they were chemically and physically alien, in ways that stretched beyond current theory. 3I Atlas, in its unraveling disintegration and mismatched volatile emissions, had become not just a mystery but a challenge, a sign that humanity's models of planetary formation and evolution remained far too narrow. And the deeper the anomaly grew, the clearer it became that the object was steering the scientific community toward a revelation not yet fully articulated, that the galaxy contained worlds built from ingredients, temperatures, and processes profoundly more diverse than the solar system ever suggested. As astronomers worked to reconcile the mounting contradictions in the chemistry and behavior of 3I Atlas, their attention gradually shifted from its present instability to its distant past. If the object insisted on behaving like nothing born beneath the sun's influence, then its origins must lie in a place where the rules were different, where temperatures fell lower, where chemistry took unfamiliar paths, where turbulence, radiation, and disk composition diverged from the solar system's formative environment. The only way to understand the strange CO₂-rich burst was to imagine the landscape of the star system that had shaped it millennia before its lonely drift into interstellar darkness. The first clues came from its volatility hierarchy. In the solar system, cometary birthplaces align cleanly with temperature gradients. The colder the region, the more exotic the ices that survive. Water forms closer to the star carbon monoxide farther out, and everything else falls somewhere in between. Yet 3I Atlas bore a signature that inverted that familiar sequence. CO2 sat in dominant abundance near the surface, while water remained a faint, reluctant trace. If this hierarchy reflected its natal environment, then its birthplace must have been colder, perhaps significantly so cold enough that CO2 froze in quantities uncommon around the Sun, and cold enough that water never dominated the composition of planetesimals. This scenario pointed towards stars smaller and dimmer than the Sun. Red dwarfs, low-mass Emit-type stars possess protoplanetary disks that extend into deep cold at relatively short radii. In such systems, the temperature gradient compresses the zones of volatile condensation, making CO2-rich ices more prevalent. Around these faint stars, water ice is still present, but carbon-bearing volatiles occupy a larger fraction of the disk's solid inventory. If 3I Atlas formed in the outer regions of a red dwarf system, its chemistry could naturally skew toward carbon dioxide enrichment. The deeper one travelled into such a disk, the more the temperature fell into the range where CO2 and CO condensed efficiently, forming layers distinct from those in sun-born comets. But birth around a red dwarf was only the first of several plausible origin paths. Another possibility pointed toward carbon-rich stars, rare but chemically intriguing objects whose atmospheres contain more carbon than oxygen. In those environments, protoplanetary disks develop chemistry fundamentally different from that of the Sun. Carbon-based compounds dominate early dust grains, and the icy mantles forming around those grains reflect the carbon-heavy balance. CO and CO2 condense readily, Complex organics emerge in abundance. Water ice may exist, but does not assume the structural importance it does in oxygen-rich systems. A planetesimal born in such a disk might accumulate volatiles in proportions alien to solar system intuition. The dust composition of 3I Atlas matched aspects of this model. Its particles displayed strong signatures of carbonaceous material mixed with amorphous silicates and organic-rich grains. Though not definitive, this hinted at a formation environment where carbon chemistry played a central role, either because the star itself was carbon-rich, or because the disk was enriched by materials inherited from earlier generations of stars. A third possibility involved the turbulent outskirts of a massive protoplanetary disk. In some young systems, gravitational instabilities cause rapid cooling in localized regions, cold shocks capable of freezing CO₂ in massive clumps. If 3I Atlas formed in such a region, the layering of CO₂ within its interior might reflect episodic freezing events. Each shock could have laid down a separate stratum of CO₂, later buried by dust and other volatiles. Such stratification would produce the repeating chemical signature observed during the object's disintegration, multiple CO₂-rich layers exposed sequentially as the nucleus unraveled. Yet this hypothesis required a star with enough mass to generate such turbulent dynamics, perhaps an F-type or A-type star whose disks are known to exhibit pronounced shock fronts. These bright hot stars generate intense ultraviolet radiation, which might explain the presence of certain complex organics preserved beneath shielding layers within the object. But such stars also shorten disk lifetimes, limiting the window for planetesimal formation. If 3I Atlas formed there, it would represent a rare survivor of rapid accretion in an unstable environment. Another line of inquiry pointed toward binary systems. These dynamic environments are fertile grounds for unusual planetesimal formation. The gravitational interplay between two stars can stir a disk in unpredictable ways, driving shocks mixing chemistry and producing temperature extremes at irregular intervals. In some binary systems, CO₂-rich regions might develop rapidly and persist longer than water-dominated layers. And once formed planetesimals in such systems are prone to ejection. Gravitational kicks can easily fling small bodies out of their birthplaces and into interstellar space. If 3I Atlas originated in such a system, its unusual chemistry might reflect the turbulent, uneven conditions of its formation, but the most intriguing models came from simulations examining the outermost zones of giant star systems regions, where temperatures drop low enough for exotic ices to condense, but where radiation from the aging star eventually strips away water ice, leaving behind more resilient volatiles. In such systems, CO₂ can remain abundant while water disappears. If 3I Atlas formed early in such a disk, then spent millions of years in a cold zone before ejection, its chemistry might match the strange imbalance observed today: CO₂ in abundance water, in depletion, and carbon monoxide only faintly present. The dust composition could reflect the aging star's influence with silicate grains coated in thick carbonaceous mantles. Yet this scenario raised a haunting possibility. What if 3I Atlas was a relic from a dying system ejected during the chaotic restructuring of planets, orbiting an aging star? If so, the object drifting through the solar system was not simply a primordial planetesimal, it was a survivor of cosmic upheaval, a fragment cast out during the collapse of its homeworld stability. Across all these models, one common thread emerged: no known solar system environment could have produced such a body. Its chemistry, layering, fragility, and volatile hierarchy all pointed toward a birthplace alien in the truest sense, not merely foreign, but forged in processes humanity had not yet fully studied. Even the object's long interstellar drift held clues. Its exposure to cosmic rays for millions of years should have erased many of its volatile features. Yet some models suggested that if the object's initial CO₂ layers were sufficiently thick, cosmic ray erosion might sculpt a protective shell, an irradiated carbonaceous crust that sealed its interior like the rind of a fruit, preserving the rich volatile reservoirs beneath. This crust, once fractured near the Sun, could allow CO₂ to escape with sudden force matching the observed eruption. In every scenario, the origin story of 3I Atlas grew more dramatic. Whether it was born around a red dwarf sculpted in a carbon-rich disk, forged in turbulent shock zones expelled from a binary system, or ejected from a dying star, each possibility painted a portrait of a world profoundly unlike the solar system. Its strange CO₂-rich burst was not an anomaly. It was a message, a chemical whisper from a star humanity had never seen, telling the story of conditions so different that the solar system's familiar physics could no longer serve as a universal map. In unraveling that whisper, astronomers found themselves forced to expand their concept of planetary diversity. 3i Atlas was more than a visitor. It was a window, and the world it revealed was vast, cold, carbon-rich, and wildly unfamiliar. As the unraveling portrait of 3i Atlas grew stranger, the scientific conversation inevitably crossed the threshold from observation into speculation, a region where theory stretches into the darkness beyond confirmed data, guided not by certainty, but by the faint contour of possibility. For the behaviour of the interstellar visitor had departed so far from the familiar that standard cometry models could no longer contain it. To understand the strange CO₂-Rich burst, researchers began exploring more exotic explanations grounded in real physics, but reaching into the frontier zone where astrochemistry, cryogenic physics, and planetary formation theory intersect with the unknown. One of the earlier speculative avenues explored the nature of the CO₂ itself. Carbon dioxide forms easily in molecular clouds and protoplanetary disks, but its survival in near-surface layers after millions of years in interstellar space is far more difficult to explain. Some researchers proposed that the CO₂ in 3i Atlas may not have existed purely as simple ice. Instead, it could have been embedded within unusual molecular matrices structures formed under conditions so cold and so chemically rich that the molecules arrange themselves in forms rarely encountered in the solar system. These matrices might include CO₂ mixed with organic polymers, frozen into complex networks during the volatile rich accretion phase of the object's formation. In such configurations, CO₂ molecules could become trapped within lattice-like frameworks of carbon chains or embedded in amorphous mixtures of methanol, methane, or nitrogen-rich ices. These compounds are stable at extremely low temperatures, but capable of releasing CO₂ explosively when warmed, particularly if the surrounding ice structure undergoes collapse. A related hypothesis explored the impact of cosmic ray alteration. During interstellar drift stretching perhaps tens of millions of years, cosmic rays continually strike icy bodies, splitting molecules and forging new ones through radiolysis. This process can create an array of exotic compounds, carbon suboxides, long-chain organics, nitriles, and highly reactive radicals. If 3i Atlas contained layers rich in these radiolytically altered materials, the warm-up near the Sun could have triggered chemical breakdowns that release CO₂ in sudden bursts. In this context, the CO₂ plume might not reflect the original composition alone, but a secondary chemistry activated by long-term radiation exposure. Speculation also touched on clathrate structures, molecular cages formed when water ice traps gas molecules within its crystalline framework. Clathrates are common in planetary bodies with cold surfaces such as Titan or certain Kuiper belt objects, but in the extreme temperatures of distant protoplanetary disks, clathrates could form under conditions unseen in the solar system, potentially trapping CO₂ in large quantities. If 3i Atlas were rich in such CO₂-laden clathrates, then a structural collapse or thermal activation could release CO₂ in a disproportionate burst matching the observed chemical signature. More daring theories proposed chemical environments even further from solar system models. Some researchers suggested that 3i Atlas could have formed in a disk enriched by the remnants of a carbon-rich supernova. Carbon-enhanced materials from such a progenitor could create icy bodies with volatile distributions starkly different from those of the Sun's disk. In such regions, CO₂ might dominate not as a secondary component, but as a primary volatile condensing in thick layers, or forming complex compounds that later destabilize under radiation or heating. If true, then 3i Atlas might be a relic of a system shaped by the ashes of stellar death, rather than the quiet accretion of a stable disk. Still others explored the role of pressure. Deep within certain protoplanetary environments, especially turbulent regions near shock fronts or dense zones in binary systems, volatiles can become trapped under pressure during formation. If 3i Atlas contained pockets where CO₂ ice formed beneath the layers of dust or frozen organics, then those reservoirs might have remained sealed throughout interstellar drift. When the Sun's heat reached them, the pressure differential could have driven an eruptive release, producing a jet powerful enough to alter the object's rotation and trajectory. Another frontier of speculation examined the possibility that 3i Atlas might not be a simple planetesimal at all, but a fragment of a larger differentiated world. If it had once been part of a dwarf planet or moon with internal cryovolcanism, stratified ice layers could have accumulated over geological timescales, layers that later shattered during a catastrophic ejection event. In this scenario, the CO2 burst could reflect an ancient cryovolcanic reservoir, a remnant of internal activity that had once reshaped the surface of a small alien world. While dramatic, this idea gained traction from the object's apparent heterogeneity and the sequential exposure of distinct chemical layers during its fragmentation. A more subtle but equally profound hypothesis considered the early dynamics of chemical evolution. In many protoplanetary disks, volatile chemistry does not evolve smoothly. Instead, it undergoes periodic disruptions, freeze-out events when temperatures fall rapidly, or transient warm-up phases driven by stellar flares or disk instabilities. These cycles can forge chemical gradients that fossilize into the planetesimals forming within them. If 3I Atlas emerged from such a volatile, dynamically variable region, then its CO2-rich layers might represent a frozen record of multiple chemical epochs, each one leaving its imprint on the body's internal architecture. A final, elegant possibility suggested that the CO2-rich burst resulted from a feedback loop between thermal fracture and volatile release. As sunlight warmed one region, CO2 would sublimate, expanding into cracks and forcing them wider. The cracks, once widened, would expose deeper CO2-rich layers, triggering additional sublimation. This self-amplifying process could explain the sustained imbalance in volatile emissions long after the initial burst. It also hinted at a cascading failure within the nucleus one that might continue until the object disintegrated completely. Though speculative, these theories shared a common thread. All proposed that the true strangeness of 3I Atlas lay not in its sudden eruption, but in the ancient chemical environments that had shaped it long before it entered interstellar space. The burst was merely the first revealed layer of a deeper, more complex history, a history encoded in molecular structures, exotic ices, and the physics of frozen worlds born under unfamiliar skies. In exploring these possibilities, astronomers found themselves confronting an unsettling implication. The diversity of small bodies in the galaxy was far wider than previously imagined. The solar system, with its water-dominated comets and predictable volatile patterns, represented only one narrow expression of planetary chemistry. Elsewhere in the unexplored reaches of the galaxy, worlds might form with entirely different priorities: carbon-first planets, nitrogen, heavy moons, or volatile-rich objects built from ices unknown to the Sun. 3I Atlas, with its impossible burst, was a reminder that the universe is not bound by our expectations. It was an emissary from an alien chemistry, a messenger from a star whose language humanity had not yet learned to translate. The dust of 3I Atlas, those drifting grains dim and delicate, became a kind of forensic evidence scattered in the wake of the interstellar visitor's slow disintegration. For while the volatile gases revealed the chemistry of its outer layers, and the CO2-rich burst exposed the hidden reservoirs within the dust, carried an even older story. Dust does not merely record recent activity. It often contains the imprints of processes that shaped a body at birth, endured cosmic ages, and survived the harsh weathering of the interstellar void. In the case of 3I Atlas, its dust became the key to understanding how a fragile shard of another star's nursery could drift through the galaxy for millions of years and still retain a volatile heart. Dust in astronomical terms is the oldest storyteller. It carries fragments of minerals, organic compounds, ices, and irradiated residues. It forms in stellar atmospheres, in supernova debris, in the swirling chaos of young circumstellar disks. When astronomers examined the dust shed by 3I Atlas, they did so with a reverence normally reserved for relics, because this dust had formed under a different sun, in a chemical environment the solar system could not replicate. At first glance, the dust cloud of 3I Atlas seemed unremarkable. It was faint, lacking the broad reflective arcs of bright cometary tails. Its particles were exceptionally fine, scattering light inefficiently, leaving only a thin haze trailing the nucleus. But it was precisely this faintness that intrigued researchers. Fine dust suggests weak cohesion materials that crumble easily when heated or stressed. In the solar system, comets that have spent many cycles near the Sun often produce coarse compact grains formed through repeated heating and sintering. But 3I Atlas produced dust more akin to that of dynamically new comets, bodies making their first journey inward. Yet this interstellar object was not young. Its chemistry and structure suggested that it had wandered the galaxy for geological time. How then had its dust remained as fragile as that of a newborn comet? The most plausible answer lay in the void weathering that shapes interstellar bodies. Unlike comets in the solar system which undergo cyclic heating, interstellar objects drift in an environment so cold and so sparsely irradiated that thermal metamorphism is nearly non-existent. Cosmic rays continuously modify surface materials, breaking molecular bonds, forging radicals and layering organic residues over exposed grains, but they do not provide enough energy to anneal dust into more durable forms. Over time, the outer layers of such objects become coated with a carbon-rich patina, a darkened crust composed of complex organic molecules. Beneath this irradiated armour, however, the grains remain as delicate as the day they formed. The dust of 3I Atlas reflected precisely this duality. Spectroscopy revealed a mixture of amorphous silicates, carbonaceous material, and organic compounds, similar in some ways to the most primitive solar system comets, yet distinct in distribution and abundance. The organic signatures were unusually strong, hinting at long exposure to cosmic ray processing. Such processing can gradually convert simple molecules like methane or methanol into complex carbon chains, nitriles, or tar-like substances. When these modified grains finally escape the nucleus, they reveal a history of cold darkness stretching across cosmic distances. Yet the dust did not only reflect age, it also reflected origin. Amorphous silicates are among the most primitive materials in the universe, formed in the outflows of dying stars before being incorporated into molecular clouds. The ratio of silicate to carbonaceous grains in 3I Atlas suggested that its parent protoplanetary disk had been enriched with interstellar silicate dust, but had simultaneously undergone carbon-heavy chemistry. The presence of abundant organic-coated grains hinted at a disk that inherited materials from earlier generations of stars' elements, forged in supernovae processed in molecular clouds, and accreted in the cold outer regions where planetesimals form. But perhaps more intriguing was what the dust lacked. Microscopic analyses inferred from scattering patterns indicated a scarcity of refractory minerals that form only in hotter inner regions of protoplanetary disks. This absence strongly suggested that 3I Atlas formed far from the warmth of its star, in a region too cold for crystalline silicates or heavy metallic grains to condense. In such environments, CO2 ice could accumulate in layers dominating the volatile budget, while water ice might remain minimal. This aligned with the observed chemistry, a body forged in extreme cold, carrying the frozen breath of a distant disk. Still, void weathering leaves its scars. Cosmic rays do not merely darken surfaces, they erode them, sputtering away atoms and breaking apart molecules. Over millions of years, this process can hollow dust grains, weaken ice bonds, and create microfractures that destabilize the surface. Thus, the dust of 3I Atlas told a story not only of formation, but of erosion of centuries upon centuries spent drifting through the void, as microscopic impacts and cosmic radiation slowly etched away the object's surface layers. These grains, fragile and small, were the remnants of that process, the ashes of interstellar weathering. Dust also revealed clues about the burst itself. The CO2 plume carried fine particles into space, but the grains it carried were disproportionately tiny compared to the force of the eruption. A powerful jet should lift material from deeper layers, not only fine powders but larger aggregates. Yet 3I Atlas's dust remained uniformly small, hinting that even its interior was composed of fragile porous material. If deeper layers had been compacted or enriched with larger grains, the burst would have lifted a more diverse range of particle sizes. Instead, the uniform fineness suggested that the entire nucleus may have remained structurally primitive, never heated or compressed enough to form larger aggregates. This observation fed into a profound speculation. Perhaps the dust of 3I Atlas, shielded beneath layers of carbonaceous crust, had remained unchanged since its birth. Every grain drifting into space from the disintegrating nucleus might be a pristine fragment of the environment that existed around its distant star long ago, a direct sampling of another solar system's early chemistry. Observations of polarization, the way dust scatters, polarized light added another layer to the story. Polarization patterns can reveal the shape and porosity of grains. In the case of 3I Atlas, the pattern suggested incredibly porous grains, almost fluffy, in structure composed of aggregates of smaller particles. These are the types of grains formed in the earlier stages of planetesimal growth before compaction occurs. Their survival into the present day spoke to the interstellar object's extreme fragility and to the cold, gentle conditions under which it had formed. Even the directionality of the dust tail revealed clues. Rather than forming a smooth, curved arc shaped solely by solar radiation pressure, the dust tail exhibited subtle irregularities, signs that the grains were extremely light, influenced not only by sunlight, but also by the weak outgassing patterns of the nucleus. Such behavior implied dust densities lower than those found in nearly all solar system comets. As astronomers pieced together these signs, fine grains, porous aggregates, carbon-rich coatings, absence of refractory minerals, low-density dust, they began to see the dust of 3I Atlas as more than debris. It was a preserved relic from a world whose chemistry diverged from the sun's in profound ways. And intertwined with this scientific revelation was a subtle emotional thread. Each grain drifting away from the disintegrating nucleus represented a fragment of a place humanity would never visit, a piece of a distant star's story released into the solar system for the briefest moment. The dust was not merely material, it was a whisper, a message spoken through the most ancient matter the cosmos could offer. In the scattering of those grains drifting silently across the solar system, astronomers glimpsed not just what 3I Atlas was made of, but how profoundly different the environments of other stars must be. The dust was a map not of space, but of chemical diversity. And like all cosmic maps, it did not show roots, but origins, the birthplace of a wanderer whose strange CO₂-rich exhalation had already reshaped humanity's understanding of frozen worlds beyond the sun. Long after the initial discovery of 3I Atlas and its startling CO₂-rich exhalation, the effort to understand the interstellar visitor had become a global astronomical campaign. Its fragility, its erratic rotation, its mismatched volatile ratios, and the strange dust it released had transformed it from a curiosity into a priority target, an object whose brief life within the solar system would offer humanity one of its rare chances to study matter, forged under the light of another sun. Every available scientific tool was turned toward it, from ground-based telescopes to spaceborne observatories, from wide-field surveys to specialized spectrographs, tuned to isolate faint chemical lines embedded in sunlight reflected from the fragmenting nucleus. The instruments that first noticed 3I Atlas, wide-field survey telescopes like Atlas Pan-STARRS, and the Zwicky Transient Facility handled the early work mapping its trajectory, brightness, and fragmentation pattern. But once the strange CO₂ signature emerged, the observational hierarchy shifted. This was no longer the passive tracking of a faint interstellar trespasser. It became an active interrogation, with each instrument chosen to reveal a different layer of the mystery. High-resolution spectroscopy became the backbone of the campaign. Instruments such as Keck's NIRSpec, the Very Large Telescope's X-Shooter, and Subaru's IRCS turned their narrow fields toward the dim visitor. They decomposed the object's faint light into spectra detailed enough to reveal the molecular fingerprints of the gases escaping from its fragile body. These instruments confirmed the dominance of carbon dioxide, but also highlighted subtler signals: the faint traces of carbon monoxide, the near whisper of water vapor, and the peculiar ratios that refused to match solar system expectations. Each spectrum was a snapshot of the object's evolving state. In the wake of the first CO₂ blast, the spectrum changed not smoothly, but in abrupt shifts that hinted at new layers being exposed, new fractures opening, and deeper chemistry awakening. Some nights the emission lines flared momentarily, then faded. Other nights the dust signature weakened while the gas lines strengthened. The tools tracking 3I Atlas were witnessing a body unraveling in real time. Space telescopes added another dimension. The Hubble Space Telescope provided high-contrast imaging that revealed the fragmentation of the nucleus with clarity unavailable from the ground. Its wide ultraviolet coverage detected the delicate emission lines of OHCN and other daughter products produced when sunlight breaks apart escaping molecules. Hubble's precision showed how asymmetric the dust distribution had become, how different fragments had begun their own paths through space, each carrying a fraction of the original object's mass. But perhaps the most powerful new addition was the James Webb Space Telescope. Still early in its scientific life, JWST turned its infrared eyes toward the object, capturing data no prior interstellar visitor had ever offered. Through Webb spectroscopy, astronomers glimpsed the thermal signatures of the nucleus, revealing its temperature distributions and hinting at internal structure. Webb's sensitivity to complex organics allowed it to detect the faint fingerprints of carbon-based compounds in the escaping dust signatures, consistent with the long-term cosmic ray processing that the object would have endured across interstellar space. The thermal measurements were especially revealing. JWST showed that portions of the nucleus responding to sunlight warmed rapidly, while others remained locked in deep cold. This thermal disparity supported the idea that the object's interior consisted of different classes of volatile materials, each responding to heat through different pathways. In some regions, heat penetrated only millimeters. In others, shallow fractures drew warmth deeper, activating volatile pockets beneath the crust. The object's fragility and chemical imbalance were being mapped not only by spectrographs, but by the infrared glow of its decaying structure. Meanwhile, radio observatories entered the effort. Facilities like ALMA, designed to peer into the cold chemistry of distant galaxies, began analysing the faint signature of gas molecules escaping from 3I Atlas. Although the object was faint for millimeter-wave observations, ALMA detected subtle transitions in CO and CN, contributing critical data points to understand the evolution of the coma. These radio signatures helped refine models of gas flow, demonstrating that the CO2 burst was not followed by a smooth decay, but by intermittent venting from multiple locations. Each tool revealed a different facet of the story, but the deepest efforts lay in synthesis, combining delta across wavelengths, across continents, across orbital platforms. Collaborative teams formed spontaneously. Astronomers from Chile, Hawaii, Europe, and space agencies across the world pooled observations to create a temporal map of 3I Atlas unraveling. They tracked how certain fragments brightened or dimmed, how the dust tail shifted, how the volatile emissions evolved from hour to hour. In parallel, theoretical groups used these observations to test their models. Thermal inertia simulations were fed new data daily. Chemical evolution models were adjusted to reflect the latest spectral findings. Volatile transport simulations explored how CO2 might migrate through porous matrices under sudden heating. Dust dynamics models attempted to replicate the faint drifting particles observed by Hubble. Even gravitational models were refined to calculate how the object's disintegration affected its hyperbolic escape trajectory. In many ways, the tools tracking 3I Atlas represented not just the capabilities of modern astronomy, but its philosophy, a recognition that the cosmos offers fleeting opportunities, and only by uniting instruments across wavelengths can humanity capture the full story of a transient interstellar guest. Ground-based telescopes revealed the visible drama fragmentation brightening dust tails. Space telescopes revealed the chemistry CO2 dominance, organic rich dust thermal anomalies. Radio arrays revealed the deeper gas structure, and all of them together formed a portrait far richer than any one observatory could have provided alone. But for all their power, the tools were still limited by distance. No spacecraft could approach the visitor, no probe could sample its surface. The scientific community felt acutely the absence of a dedicated interstellar interceptor, something fast enough, responsive enough to reach such objects before they disintegrated or disappeared into the dark. As 3I Atlas continued to crumble under the sun's heat, it became a symbol of both human progress and human limitation. A reminder that the universe still holds mysteries that no telescope, no matter how advanced, can fully grasp at a distance. And yet the pursuit continued, driven by urgency. With each day, the object grew fainter, its fragments scattering its volatiles, dissipating into the void. The tools tracking it captured every trace they could, every spectral line, every thermal shift, knowing that each observation was a page in a scientific chronicle that would never again be repeated. The effort to decode 3I Atlas had become a race against time, a final attempt to preserve the story of an object that had travelled farther than any spacecraft borne witness to conditions unseen by human eyes, and revealed its nature only in the instant of its destruction. In that race, the instruments of modern astronomy performed not merely as tools, but as extensions of human curiosity reaching into the cold alien silence of the interstellar traveller before it slipped forever beyond the sun. Even as telescopes strained to capture the fading traces of 3I Atlas, the scientific conversation shifted from observation to anticipation, from the urgent cataloguing of a dying interstellar visitor to the realization that future wanderers would come each carrying their own alien chemistry, each demanding tools far more capable than those humanity currently possessed. The passage of 3i Atlas illuminated in stark detail the limitations of earthbound and orbital instruments. It underscored the impassable barrier of distance, no matter how sensitive a spectrograph might be, or how refined a thermal model. Nothing could compensate for the absence of a probe able to intercept an interstellar object directly. The science extracted from 3i Atlas was profound, but it was also incomplete piecemeal fragments of a narrative reconstructed from afar. Out of this recognition emerged an intensified global interest in future interstellar missions. The scientific community began re-examining concepts that had long lingered in white papers, conference sessions and mission proposal archives, fast response probes, solar sail interceptors, nuclear electric craft and gravitational slingshot trajectories designed to chase down or rendezvous with interstellar visitors before they disappeared into the darkness beyond Neptune. The lessons learned from Oumuamua Borisov and now 3i Atlas converged into a single imperative: humanity needed the capability to reach such objects while they were still intact. Even before 3i Atlas, one of the most prominent concepts was ESA's proposed comet interceptor, a mission designed not for a predetermined target, but to wait poised in deep space until a visitor appeared. The craft would sit near the L2 Lagrange point, ready to engage its engines and rendezvous with a newly discovered comet or, with luck, an interstellar body. But Comet Interceptor was limited in speed. It could not match the extreme velocities of most interstellar visitors. Had it existed during the passage of 3i Atlas, it would not have been able to reach it in time. Still, it represented an important philosophical shift from waiting passively for interstellar objects to preparing actively for them. NASA JPL and several independent research groups began exploring far more ambitious concepts. One of the most discussed was a solar sail or solar thermal propelled mission, capable of achieving unprecedented speeds. By diving extremely close to the Sun, closer than any spacecraft had ever risked, and using solar radiation or thermal thrust to accelerate such a craft, might achieve velocities necessary to intercept an interstellar object shortly after discovery. In simulations, such interceptors could reach speeds exceeding 20% faster than conventional propulsion methods. But even these designs required extraordinary precision. An interstellar object discovered late in its inbound trajectory might leave too little time to launch a line and accelerate a spacecraft to intercept it before it escaped again into the starless beyond. Another proposal developed in theoretical mission studies involved nuclear electric propulsion. With sustained thrust and high efficiency, a nuclear-powered interceptor could gradually accelerate to the velocities necessary to chase down distant visitors. While slower to reach peak speed than a solar thermal craft, nuclear propulsion could maintain acceleration for months or years, potentially making it ideal for missions targeting interstellar objects early in their inbound approach. These concepts were not mere fantasies. They drew on engineering foundations from past studies into missions for the outer planets and interstellar precursors. Beyond propulsion, researchers explored new survey technologies to identify interstellar objects far earlier than Atlas or Pan-STARRS could. The upcoming Vera C. Rubin Observatory, with its sweeping all-sky scans, promised to detect faint, fast-moving objects at unprecedented distances. Its legacy, Survey of Space and Time LSST, would map the sky repeatedly, capturing the subtle shadows of small, rapidly moving bodies long before they approached the inner solar system. If Rubin had been operational before the arrival of 3i Atlas, it might have detected the visitor months earlier, giving astronomers more time to orchestrate coordinated observations, or in some imagined future scramble, an intercept a probe. Rubin's capabilities raised hopes that future interstellar visitors would not arrive as surprises, but as early heralds detected while still beyond Jupiter's orbit, offering precious months to study their trajectories and chemistry before they came close enough for detailed observation. Simultaneously, mission designers revived the dream of interstellar precursor probes, spacecraft sent not to specific objects but outward into the realm of the outer planets, and beyond, ready to make opportunistic flybys of interstellar debris crossing their paths. Such probes could host dust analyzers, spectrographs and particle detectors capable of sampling material directly. If one of these precursors drifted into the path of an inbound or outbound interstellar traveler, humanity might capture data impossible to obtain from Earth. But among all the concepts discussed in the wake of 3i Atlas, the most ambitious and the most philosophically stirring was the proposal for a craft capable of meeting interstellar objects outside the solar system entirely. These interstellar rendezvous missions envisioned spacecraft travelling into the galactic neighbourhood, cruising the vast expanse between stars, sampling interstellar dust, and positioning themselves to encounter objects like 3i Atlas before they ever encountered the Sun. Such missions were decades away, even in theory, requiring breakthroughs in propulsion and energy systems. Yet they represented the next logical step if interstellar objects were messengers from distant planetary nurseries, then meeting them on their own terms, far from solar interference, would reveal their chemistry in its purest state. Still, even modest advances could transform the scientific landscape. Instruments capable of remote cryogenic analysis might read volatile signatures at greater distances. Space telescopes dedicated to cometary spectrography could monitor emissions continuously as interstellar objects approach the Sun. Small rapid-response cubes at interceptors launched alongside large emissions, or maintained in stable solar orbits, might dash toward new arrivals, taking measurements in their final days of coherence. These tools would not merely help understand interstellar visitors, they would help categorize them. If multiple objects like 3i Atlas were observed closely enough, astronomers could build a taxonomy of interstellar bodies, linking chemistry to star types, volatile layers to planetary system architecture, dust composition to stellar evolution. Each visitor could become a data point in a galactic map of planetary diversity. For now, however, the tools remained aspirational. The telescopes tracking 3i Atlas were the best humanity had vast mirrors atop mountains, orbiting observatories at Lagrange points, radio arrays stretched across desert plateaus. But the object's strange CO₂ breath made clear their limits. Without a probe to sample its surface, without an interceptor to approach its nucleus, 3i Atlas would forever remain partly unknowable. Yet this unknowability did not diminish the scientific pursuit, it sharpened it. The strange CO₂ burst was a challenge, a catalyst urging humanity to build faster craft, deeper sky surveys, smarter spectrographs and missions capable of reaching the next wanderer in time. The best tools available had captured the story of 3i Atlas as fully as distance allowed. The next tools forged from the lessons of this encounter would reach further, for in the cold light of telescopes tracking its dissolution, 3i Atlas offered a simple, profound truth the galaxy is sending emissaries. And if humanity wishes to learn from them, it must be ready not with what it has, but with what it must still create. Long before its fragments faded into the deepening distances of space, 3i Atlas had already begun to imprint itself upon the scientific imagination. It had arrived as a faint point of light revealed itself through a single impossible exhalation of carbon dioxide unravelled under the sun's warmth, and departed in a cascade of dust so fragile it scarcely glimmered. But the consequences of that brief appearance, those spectral lines, those dust grains, those contradictory ratios extended far beyond the object itself. They reached into the foundations of planetary science, unsettled long-held assumptions, and forced astronomers to consider that the solar system's familiar chemistry may not represent the galaxy's norm, but only one example of a vast and diverse chemical tapestry. The most immediate consequence arose in models of comet formation. Before 3i Atlas, the diversity observed between solar system comets seemed broad but comprehensible. Variations in water, carbon monoxide, methane, and organic compounds were expected. Even deviations like hypervolatile CO jets or nitrogen-rich comet could be explained by differences in formation temperature or early collisional history. But a sustained CO₂-dominated outburst, unaccompanied by comparable water release, simply did not fit that spectrum. It required temperatures so low and chemical histories so unusual that comet models built around the Sun's disk had to be expanded into parameter spaces that had rarely been explored. This expansion reshaped the concept of a typical planetesimal. Instead of assuming that most comets in the galaxy resembled those of the solar system, water-rich, dust-layered, fragile but chemically predictable researchers now recognized that such assumptions were grounded only in local experience. If CO₂-dominated bodies could form naturally in carbon-enhanced disks or ultra-cold regions around dim stars, then a significant fraction of exoplanetary systems might host planetesimals with volatile signatures radically different from those humanity had studied. The chemistry of worlds became less monolithic, more pluralistic. The galaxy grew chemically larger. A parallel shift occurred in theories of planet formation. Comets serve as probes of their natal environments. They carry chemical fingerprints of the disks in which they formed. 3I Atlas forced astronomers to reconsider the range of temperatures and compositions within protoplanetary disks across the Milky Way. If CO2 could accumulate in such abundance, then the outer regions of some disks must be far colder or far more carbon-rich than models typically allow. This in turn suggested that planets forming in such disks might have atmospheres or crustal chemistries dominated by CO2, rather than water worlds with thick carbon dioxide ice mantles, or atmospheres that mirror early Venus but formed in the cold, not the warm. The implications extended to habitability. If planetary building blocks vary this widely, then the chemistry of emerging worlds could diverge dramatically. Some systems might produce water-poor worlds by default. Others might form planets with volatile cycles unfamiliar to terrestrial experience, CO2 oceans, nitrogen glaciers, or organics-rich crusts shaped by cosmic ray chemistry. The standard model of rocky planet formation built around water as a universal volatile foundation became less certain. The building blocks of other stars were revealing themselves to be stranger, more varied and less constrained by the blueprint of the Sun. 3I Atlas also challenged the understanding of interstellar evolution. Before its arrival, the expectation was that cosmic rays and ultraviolet light would strip interstellar objects of their upper, volatile layers, leaving desiccated surfaces and depleted shallow reservoirs. Oumuamua had supported this assumption with its volatile silence. But 3I Atlas contradicted it dramatically. Its CO2-rich eruptions suggested that some interstellar objects retain significant volatile mass near their surfaces, either because they begin their journeys with unusually thick deposits, or because the processes of interstellar weathering preserve certain volatiles better than expected. This forced researchers to re-examine cosmic ray processing not as a universal eroder, but as a process whose outcomes depend heavily on initial chemistry. A crust formed from carbon-rich organics might act as a shield, preserving deeper layers far longer than water-dominated crusts would. This possibility altered the perception of how long small bodies can survive in interstellar space, and what they carry with them when they arrive. Dust studies from 3I Atlas deepened this re-evaluation. The fragile, porous, radiation-darkened grains it shed were among the most primitive ever observed. Their presence demonstrated that interstellar travel does not necessarily compact or anneal dust. Instead, it may preserve delicate aggregates that never experienced the thermal processing common in solar system comets. This insight had profound implications for models of interstellar dust composition, suggesting that some fraction of the dust drifting through the Milky Way may be composed of similar fragile grains, material nearly unchanged since the birth of ancient stars. These consequences cascaded into astrophysics more broadly. If small bodies like 3I Atlas are common, each carrying distinct chemical histories, then interstellar objects may represent a vast unrecognized archive of galactic diversity. A single object could act as a sample return mission from a distant star system, offering clues to disk chemistry, stellar evolution, and the early conditions that shaped alien worlds. The discovery of even one such visitor redefined the galaxy not as a distant theoretical environment, but as a place physically connected to the solar system through these drifting messengers. But the most profound consequence was philosophical. 3I Atlas reminded humanity that the solar system is not the template for planetary systems, but merely one instance among countless possibilities. Its strange breath, its CO2-dominated exhalation was not an anomaly but a revelation. A sign that the galaxy's worlds are sculpted by diverse temperatures, chemistries, and stellar stories. A reminder that human understanding of planetary formation remains narrow, bounded by the Sun's specific conditions. In its brief life near the Sun, the interstellar wanderer expanded the boundaries of what scientists consider possible. It revealed a cosmos in which carbon dioxide might dominate the surfaces of frozen bodies, where dust remains unaltered across millions of years of drifting darkness, where chemical reservoirs form under alien skies, and where each visitor carries the memory of a world humanity cannot reach. And as its fragments scattered into the void, 3 Atlas left behind a clear, humbling consequence, that the galaxy is richer, stranger, and more varied than any model built around the solar system alone could ever predict. In the final weeks of its passage through the solar system, as the fragments of 3I Atlas drifted into a widening cloud of dust and molecular vapor, astronomers found themselves turning from data toward meaning. The object had delivered its message through spectra, through dust, through an impossible burst of carbon dioxide that refused to fit the familiar architectures of cometary behaviour, and now it was fading, dissolving into the very darkness from which it had come. The telescopes followed it as far as they could until the last grains vanished into distances that no optical mirror could penetrate. And as the light slipped away, a quieter question emerged. What does it mean for humanity to witness such a thing, a visitor shaped by another sun disintegrating beneath ours? The question stretched beyond chemistry, beyond spectral lines, beyond volatile hierarchies. It reached toward the emotional core of astronomy, the tension between the vastness of cosmic time and the brevity of human perception. 3I, Atlas, had travelled through the interstellar medium for millions of years, drifting between stars with no witness, no story, no audience. In all that time it had remained cold, inert, a fragment of a world long vanished, or a disk long dissipated. And then for a brief moment, an instant on cosmic scales, it passed through the realm of the sun awakened by warmth, illuminated by telescopes unravelling its secrets just long enough for human minds to take notice. There is a poignancy in that contrast, a worldless fragment carrying the chemistry of an unseen star encountered by another civilization for only the shortest of intervals. The strange CO₂-Rich burst the improbable survival of fragile ices, the dust that held stories older than the age of human species. All of it was revealed only because the sun warmed an object that had never expected warmth again. In its disintegration, 3I Atlas became a metaphor for the fragility of cosmic memory. The layers within its CO₂ strata, amorphous ice matrices, carbon-bearing dust, were geological sentences written at the dawn of some distant system's birth. For millions of years, those sentences remained sealed within the nucleus, untouched by sunlight, preserved in a hush deeper than any found in the solar system. Only when the object entered our domain did those sentences break open. The CO₂ burst was not only a physical event, it was the sudden release of a cosmic biography written in volatiles instead of ink. The philosophical weight of this realization deepened as astronomers reflected on the object's chemical alienness. If 3I Atlas could contain such unusual volatile structures, how many more varieties of matter wander the galaxy unseen? If its birth environment differed so profoundly from the sun's, what does that say about the diversity of planetary systems, about the billions of worlds forming under temperatures, pressures and chemistries the solar system has never known? The object's dust, fragile and porous, whispered an answer that the galaxy is full of worlds humanity has never imagined. Worlds where CO₂ ice forms first, not water. Worlds shaped in disks enriched by ancient supernovae. Worlds illuminated by stars cooler, dimmer, redder, or more chaotic than the sun. Worlds where the building blocks of comets follow rules unknown here. Worlds whose fragments, like 3I Atlas, carry volatile memories that do not obey solar system expectations. In this sense, the interstellar visitor did more than challenge scientific models. It expanded the emotional horizon of astronomy. It suggested that the Milky Way is not simply a collection of distant points, but a living network of chemical stories, each one written in dust and ice, each one drifting freely between stars. Humanity may never travel to the birthplace of 3I Atlas, but through the object's breath, it glimpsed the possibility of worlds far colder, deeper and older in their chemistry than anything orbiting the sun. There was also a humbling reminder woven through its dissolution. Even with the most advanced telescopes, even with the extraordinary sensitivity of spaceborne observatories, much of the object remained unknowable. The deeper chemical layers, the exact structure of its volatile pockets, the precise architecture of its fractured nucleus. These details vanished when the object disintegrated. It was a reminder that the cosmos often grants knowledge in fragments, in glimpses, in partial revelations, that the stories it tells are sometimes incomplete, and that understanding often arrives with jagged edges. Yet even incomplete stories hold meaning. 3I Atlas arrived without warning, offered a burst of alien chemistry, and departed forever. It forced humanity to reimagine the diversity of the galaxy, to consider that planetary systems evolve under conditions far stranger than those familiar to Earth. It challenged assumptions, stretched theories, and invited questions that will shape future missions and telescopes yet to be built. And as the last traces of the interstellar visitor drifted into silence, it left behind a sense of kinship, quiet, distant but unmistakable. A kinship born not of familiarity but of recognition, that across the light years countless fragments wander, each carrying stories of worlds unseen, each waiting for the warmth of a foreign star to speak. In that recognition lies the deeper meaning of 3i Atlas. It was not merely a comet-like body, not merely a carrier of unfamiliar volatiles. It was a reminder that the universe is always larger than the models made to explain it, always, stranger than the expectations held by those who study it. And in its sudden breath of CO₂, violent, ephemeral, beautiful humanity, glimpsed the truth that even the smallest wanderer can expand the boundaries of knowledge. As the interstellar fragments dispersed into the long dusk beyond the planets, the story of 3i Atlas softened. Its sharp spectral lines faded, its dust cloud thinned, and the heat that once awakened it receded into the cold. The observatories turned their mirrors toward new regions of sky, but the faint memory of the object lingered like a trail of quiet thought. The urgency of discovery gave way to reflection, and in that gentler space the visitor's message took on a calm, almost soothing clarity. The universe, the object seemed to whisper, is vast enough to hold countless forms of ice and dust, each shaped by the quiet labour of distant stars. There is no single template for worlds, no universal sequence for their growth or decay. There are only variations, gentle, intricate and enduring, written across the galaxy, in materials older than planets themselves. And though such wanderers may fracture and disappear, their lessons remain carried in the instruments and minds that recorded them. In the long hush that followed its dissolution, 3i Atlas offered not mystery but assurance. Assurance that curiosity will always find new frontiers, that even the smallest fragment can reveal truths unreachable by larger bodies, that distant suns, though unseen, still leave their fingerprints upon the matter they form, and that the solar system is not alone in its patterns, but part of an immense, varied, quiet chorus of worlds. As the last traces of the interstellar visitor slipped beyond sight, the sky remained serene. The stars resumed their steady glow and the planets continued their patient orbits. And somewhere in that calm, a sense of gentle wonder settled a reminder that the universe is wide, its stories unending, and that every wandering shard carries with it the soft echo of another home. Sweet dreams.